very happy to present Yiannis Vlassopoulos, who will talk about a proposal for the mathematical structure computed by large language models. Thank you very much.
Thank you very much, Carlos. Okay, so first let me thank the organizers for this very interesting conference, and Carlos, Ernesto, and of course Ludwig. So what I want to talk about is not it's basically about what is the so when we train large language models, what we use as input is just sequences of symbols, words, and probability of next word in the sequence. So for every sequence, we have a probability distribution, and we choose from that probability distribution the next word, and then we add that word, and we keep going. The question is there some mathematical structure, some kind of symmetry encoded in this data? And you know, so this is the question that I'm going to talk about, basically. What is this mathematical structure defined by probabilities of extension of text? And it turns out that there is one, actually. And so this is what we're going to talk about. So first, let me note that computing continuations of text is a part of a very well-known and very well-studied basic structure in mathematics. So there are at least two standard ways to think about language without first thinking about probabilities. Just simplify the question. So we can think of language usually as monoids. We say, we just take two texts and we concatenate them, and then if this is part of the language, that's the result, or otherwise we put zero. Or we can use, this is a little bit less standard, but it's completely equivalent, because to consider language as a facet, as a partially ordered set, where you say that red is less than or equal to red rose. So the subtext order. And so red is less than or equal to pretty red rose. So this is you can use the subtext order, yeah.
Okay, it's a very dumb question. But how do you deal with then the symmetries with the end? Rose, red, rose. I mean, doesn't really make sense.
With symmetry?
Yeah.
With symmetry? Okay. No, yeah. So I mean, because if you have less, so what does it mean to be a facet? It means that you have to have an associativity, right? So if red is less than red rose, and red rose is less than pretty red rose, then red is less than pretty red rose also. So therefore, it's a facet. That's all.
No, but
Well,
symmetry. I mean, is it symmetric facet?
symmetric?
Yeah.
No. Facets are not. So
Exactly.
So you're saying, I mean, so you can say a pre-order. You're saying if x is less than y and y is less than x, that x has to be equal to y? There's not symmetry, I think. There's not symmetry. Just partial orders. Okay, so and actually the monoid structure and the facet structure are completely equivalent. You can go from one to the other. Basically, so all of them are categories actually. I can talk a little bit about what how you can go from the monoid structure to the facet structure. I mean, the way to do that is to consider something. I mean, you can consider both monoids and facets as categories. A monoid is a category with one object, and every morphism is just a loop, okay, of that object. So when you multiply, say pretty and red are both loops in this category, the loops of morphisms, and when you multiply them, you just compose the loops. And if you want to go from, and the facet is also a category where texts are the objects, and there's a morphism from one text to another when one is a subtext of the other. And then you can go from one to the other actually by something called the factorization construction. I'm just going to mention it because we're not going to use it, but I'm just going to mention it just to show you that they're completely equivalent. So the idea of the factorization is basically that you start with a monoid, which is the most usual construction when you're talking about categories, and you construct the facet in the following way. You take the arrows of the monoid to be the objects of the facet, and then you'd say there's an arrow between arrows when you can factorize one using the other. So for example, if you take pretty red rose, because you can factorize it using red, it's pretty times red times rose, you can factorize it, that means that there is an arrow from red to pretty red rose. So there's the factorization construction. Anyway, so that's all to say that they're equivalent constructions actually. And there's a notion in distributional semantics which says that if you want to know something about a text, the meaning of a text, you should know something about the other text around it. Okay, so texts that have similar distributions with respect to other texts have similar meaning and so on. So this idea of what are the other texts which are around, which are in the same neighborhood of a given text, is very much a standard mathematical object called an ideal. So for example, if I have a poset, well, in the case of posets, they're called upper sets or lower sets. If I have a poset, if I think of a language as a poset, if I want to take the upper set generated by red, that means consider basically all the text that contain red. And presumably, if you know all the text that contain red, that tells you something about what the meaning of red is. And if you have the monoid, the ideal is also everything that contains red, actually, because an ideal means that you multiply red by everything else, and so it contains red. So in both cases, these kind of objects tell you something about the distributional semantics says that this kind of objects tell you something about the meaning of a text. Okay, so in the case of posets, you can consider the upper set or you can consider the lower set. So for example, if you take red, you can take if you take pretty red rose, for example, you can take all the expressions that contain that, and this will be the upper set generated by it, or you can take all the expressions that are contained in it, and which will be the lower set, and both of them have something to say. And surprisingly, if you think about it in the right way, we will see that actually you can recover one from the other, even though one seems to be much larger than the other. Yeah, sorry.
So we can say that red is actually, red rose is a subset of red, and then we can say that red is actually a subset of color, and then we can say
No. It strictly has to be a subtext. So only you can say that red is less than or equal to red rose because it's a subtext.
Okay,
So
you can't escalate. So
you can escalate, but you always have to be a subtext. You cannot say that red is not a subset of the subtext of color. So red and color are not related in this poset, basically. Okay, they're not comparable in this poset. Yeah.
Although they have strong correlation.
Yes. This will appear later. Yeah, but from because this is only the beginning, right? So basically, the idea is that you want to consider upper sets and lower sets of posets as saying something generated by a text, as saying something about the meaning of the text. Yeah.
So they have to share pretty the same words to say that.
Yeah, I mean, so the way to understand that is that you can find expressions. I mean, red and color by themselves are not related, but they're both contained in red color. This is what relates them. Okay, so you can always find some bigger expression that contains both of them. If you can find some bigger expression that contains both of them, then that tells you that there is a relation between their meanings, and this is what you should recover somehow. Okay, so basically, this idea of considering upper sets, which are all the elements. Which are generated, say, by some text, which are all the elements that contain that text, or the ideal and the monoid. These are very natural structures in mathematics. Okay, they appear all the time. So, for example, when you, sorry.
I have a question. In different languages, the adjective is coming before or after.
Yeah, it doesn't matter because I haven't told you anything about. I mean, so when you take a language, all the input you take is just a text, just like the large language model. So I want to treat language just like sequences of symbols, and meaning will come later. Okay. So yeah.
But here, just to understand what's going on. In this, we have this poset.
Yeah.
And every object of the poset is a text.
Yes.
So I pick up these texts from, Wittgenstein would ask you whether a pink elephant reading Shakespeare is a text. Is this a text? Or?
Oh, okay.
So just grammatically it has to do with.
So this is where the probabilities come, right?
Mm-hmm.
This is where the probabilities come, right? Of course, the probabilities are going to choose for you what is a likely text or not.
Yeah, but we have to have a body of text too.
Oh yeah. You have a body of text, just like large language models. So just think large language models, okay? So I just want to take the assumptions of large language models and make a mathematical structure out of it. Okay, so the question is now, so how can you? So we said that distributional semantics says that the ideals or filters of the language poset of a language monoid encode something about the meaning. And By the way, let me just tell you briefly that there's a sort of duality in mathematics between algebra and geometry. That's the first level of the duality in commutative algebra. And if you have a commutative algebra, you can take the space of ideals, the prime ideals, and that space, you can think of it as, it's called a spec, and you can think of it as space on which the original algebra becomes the algebra of functions. So and you can recover one from the other. So there's a duality, fundamental duality. When you have an algebraic object and you take the space of ideals, it gives you a geometric object on which that algebra is the space of functions. So the question is, we started thinking about ideals. We haven't included the probabilities yet. We have to include it. And the question is, can we enlarge the structure, this duality between algebra and geometry, taking into account the fact that our structures are not commutative? Okay, so what would be the corresponding thing? This is what I'm going to try to develop. So if you want to check out the references, the first work on that, the rich category theory of language from syntax to semantics with Ty Bradley and John Terrilla from 2021. That's where we sort of set up the theory as an enriched category structure. And then this recently we just put this paper on the archive with Stéphane Gobert, directly metric structures arising in large language models, where it's a continuation of the previous one, but we decided not to explicitly use the language of categories so that people don't get discouraged if we don't know anything about categories. Because actually it turns out that you can write everything in sort of more geometrical texts, like the terminology like tropical geometry or metric spaces and things like that. And this team, Liu Trager, Aquile, Pereira, Zaccato, and Soato from Amazon did some experiments using this idea of ideals and so on. And they tested the semantic vectors that you get there, and they got very good results. So I'm not going to have time to talk about this now, but we can talk about this later. Okay, so, all right, so first let me set up what is the sort of fundamental structure we're going to look at. Okay, so we're going to define a probabilistic language model to be a triple, which is a poset with the subtext order, and a probability function, not normalized for the moment. So this takes two texts and gives out the probability of extension from one text to the other. And all I'm asking, the only requirement I have is that if I want to go from AI to AK, this is the product of going from AI to intermediate text AJ, and that times the probability from AJ to AK. Okay, if these three texts are comparable. Okay, just like how you do things when you have an LLM, you just pick by the condition of probability. Okay, so what is this kind of structure? Well, we're not very, or at least I was not very used to thinking about probabilities related to geometry. So, but it turns out that actually if you take minus log probability, you immediately get a geometric object, which is a metric space. And so let me immediately define the notion of a directed metric space. So this is basically a set X and the function of from X cross X to minus infinity, infinity. We're going to even take negative distances and explain how this works. But the only requirement I'm asking for is the triangle inequality. Okay, the distance from A to C less than or equal to the distance from A to B plus the distance from B to C, and the fact that the distance of an object to itself is 0. Okay, so this is a kind of generalized version of a metric space. Then immediately we see that our probabilistic language model is a special case of a directed metric space. And to do that, all you have to do is define the distance of two texts to be, if one text is less than or equal to the other, this is minus log probability of extension. And if they're not comparable, the probability is 0, so you just put minus log of 0 to be infinity. So this is infinite distance. And you can check that this satisfies the triangle inequality. It satisfies it as an equality if and only if these three texts are comparable, one is inside the other, or AI is not a subtext of AK. In that case, the distance from AI to AK will be infinite, and then the other two distances will also be infinite. If the distance from AI to AK is finite, and this condition of comparability of the elements AI, AJ, and AK is not valid, then the right-hand side, one of the terms, at least one of the terms on the right-hand side will be infinite. So basically we get this triangle inequality.
I'm sorry, could you show the previous slide?
Yes.
Okay.
Okay, So we get a kind of degenerate metric.
Why, if AI is not comparable to AK, why one of the two?
Oh, for example, if AI is not in AK, then let's say AI is in AJ. Okay, so let's say this term is finite. Well, this term has to be infinite because if AI is less than or equal to AK, then necessarily AI would also be inside AK. So that's why you can. So if AI is not inside AK and AI is not in AJ, then an AI is in AJ, then AJ cannot be in AK. Because if AJ were in AK and AI is in AJ, then AI would be in AK, and the distance from AI to AK would be also finite.
So non-comparable is from T1 and the other is 0.
Yeah, it just means non-comparable means that one is not a subtext of the other. That's all.
So
Yeah.
basically what you're saying is that your post is not connected, right? It's really not comparable, right?
Well, you can have a connected poset with non-comparable elements. It just means that they're not comparable. That's all.
But you mean first order comparable.
First order, that's right, that's right.
You mean directly one less than the other?
Directly one less than the other, yeah. But I mean, yeah, you can find a third text which is bigger than both of them. Yeah, definitely, yeah. That's what connects most things, yeah. Okay, so basically the first thing to notice is that just as a consequence of what I just mentioned is the metric determines the poset.
Very well.
Since AI is less than or equal to AJ less than or equal to AK, if and only if basically this is a kind of geodesic equation for the metric. And the distance from AI to AK is finite. And also let me notice for those of you which are sort of comfortable with category theory, but even if you're not, this directed metric space actually is a category, but it's a category enriched over minus infinity infinity. When you think of this as just the objects are just as numbers, and you're using the opposite of the usual number order for the morphisms. It has a monoidal structure which is addition. And if you write down the composition of morphisms, in that case, it becomes precisely the triangle inequality. Okay, that wasn't discovered by us; it was discovered by Bill Laver back in the 70s. That metric spaces are secretly categories enriched over zero infinity or minus infinity. Okay, so everything I'm going to do basically just follows the categorical playbook, but we're going to also interpret it. I'm going to primarily not use categorical language. Okay. So the first thing to do now is to consider, well, since I already mentioned it's a category, what we want to do is consider the unit embedding into the pre-sheaves. Okay, but what this will actually end up being is that it will be a directed metric polyhedron. So basically, we have a finite metric space, directed metric space. And in general, if you have a finite metric space, you try to isometrically embed it in the Euclidean space, you won't be able to do that. You need some sort of constraints to be satisfied. But because of the categorical interpretation of everything, actually we can find a space which is a directed metric polyhedron inside which this metric space of text would be isometrically embedded, as long as you use the right metric. So what is this metric polyhedron? It's a very simple polyhedron. The equations are just xi less than or equal to, so it's all x in R union infinity to the n, and not all the points can be infinity. I mean, everything has finite distance to itself, so nothing will have, so at least one of the coordinates will be, not infinity. But basically it's just a simple equation, xi less than or equal to xj plus dij. And there's a dual version always. One version has to do with extensions of text, and the other one has to do with restrictions of text. So there will always be two dual versions. And in the end, we will show that there's a duality theorem between them, actually. So these are the two metric polyhedra. And to explain to you where they come from, what are they really, the first thing to do is to notice that these are actually can be interpreted as non-expansive maps. If you take L with the transpose of its metric, and if you put, let me do this. And if you put this metric, the distance from S to T is D minus S, then you can check that this condition of basically the contraction condition, non-expansiveness rather, precisely tells you that this x is in PL. So a point x, this is a vector. This vector, you can think of it as a function from the metric space to scalars. Just like think about when you have a set and you think of functions on sets, they become vector spaces, right? This is exactly the analogous thing. But here, these vectors define maps, x of ai, x of aj, the distance is less than or equal to the distance from aj to ai. And you can see this immediately for easily. For example, if the distance is defined by this formula. So if you look here, for example, you see that x of ai minus x of aj is less than or equal to ai to the distance from ai to aj. So this is a condition. This is this condition here. Okay. So this is the geometric interpretation of this polyhedron. It's just a space. You start with the metric space, and then you take all non-expansive maps with respect to these metrics. Notice that the metric I want to use is not the usual Euclidean metric, but it's the maximum metric. This is determined by the category theory. So the distance between two elements of this polyhedron is the maximum of yi minus xi for all xi which are not infinite. And not all of them can be infinite, because we're taking out this case. Okay, and categorically, P of L is the category of presheaves, and P hat of L is the category of copresheaves. So this is kind of like the natural, which you have an object, just as I said, you have a set, you take the functions of the set, you get a vector space, which is a nicely behaved, much nicer object, much richer object than a set. This is exactly the same game here, but the natural way to do it is to think you start with this metric space, and the natural functions are these non-expansive maps. And the nice thing about this is, you can, as I was saying, you can embed your initial metric space into this P of L. How? Well, this is what you're embedding. So for any text AK, you take the function which gives you the distance from anything to AK. Okay. And this turns out to be an isometric embedding. This basically is the unit embedding in category theory. And dually, you can take AK and map it to the distance of AK to everything. So this lives, so if I take some red color, this lives on everything that contains red color. If I take red color, this lives on everything that is contained on red color. Okay. This seems to be quite different, but there's a duality theorem.
So up to here, L is just some set with a distance function.
Yeah, well,
with a directed metric on it. You're not using the fact that it's a language yet.
No, I'm saying this is the objects are texts, and I'm using the subtext order. So L is basically just
yeah, but I mean that could be.
It could be, yeah, absolutely.
I mean, you can do this theory.
Yeah.
Can you do this theory for any
Yes.
coset with a
Yes.
metric?
Yes. Absolutely. Okay. All right. So now the next part of the game is to understand what are the coordinates. Well, there's something called the unit lemma. It tells you precisely in this particular case, tells you that the coordinate x of ai, remember, xi is x of ai because x are considered as functions, is the distance from y of ai to x. And for those of you which are familiar with category theory, this is precisely the unit lemma. It says that this is the home, right? So if you take home of the representable functor into some other functor, this is just evaluation of x into ai. And so that's what you have to prove all these things, but you expect them to be true because of the category theory. Okay. And so now when you interpret it this way, you can see that the defining inequalities that we started with, now they have a meaning. And the meaning is that because xi is the distance from y of ai to x, and so on, this is precisely a triangle inequality. But it's a triangle inequality in the space of presheaves. Okay. So basically what this space is kind of the maximum. So you take all these maps and you just ask for the triangle inequality. Okay, so it's a convex space that is the maximally one that just satisfies the triangle inequality. And there's a dual thing as always. So remember on P of L we have the metric D on this is called the func metric, by the way, for historical reasons. defined by Funk, and it's very much related to Hilbert's metric, Hilbert projective metric. If you symmetrize it, you get Hilbert projective metric. So so here is exactly the same thing, but you just have to use the transpose metric. So you get the distance from y to y hat, and you can interpret the defining inequality for this polyhedron precisely as a metric inequality also. Okay, all right. Now, so we have our metric space of texts. We embedded that isometrically inside this nice polyhedron. Okay, and now actually it was a kind of accident of history that we had to do the metric stuff, because just people, I mean, we're not used to dealing with all these things when we do it multiplicatively. But the multiplicative picture, of course, also makes sense, right? We can just not go back to probabilities, because we took minus log probabilities to do all that. But we could just take e to the minus xi for any xi, for any x which is inside P of L, we can just take e to the minus xi. And we end up with this definition. So if we exponentiate all the coordinates, so remember we had xi less than or equal to xj plus dij. So now if we exponentiate, you get e to the minus xi, which is zi, e to the minus xj, which is zj, and e to the minus log probability, blah, blah. So it becomes, so this is the condition. The condition for this is that zi is greater than or equal to the probability to go from ai to aj times zj. Okay. Now, and by the way, notice that this is a polyhedral cone, because if you multiply by lambda, the zi is here, you still get this, the elements that satisfy this equation. So we just have a nice polyhedral cone here. And another thing is that when we saw this, I didn't know about it, but at some point I realized that this is a cone version of what's Stanley's order polytope. So Stanley, which I wish was here actually, but unfortunately he's not. He defined for any poset a polytope. And this polytope actually corresponds to precisely when these values are just 0 or 1. So if the probabilities are 0 or 1, then you get just a bunch of equations, zi greater than or equal to zj when ai is less than or equal to aj, and that's Stanley's polytope. Okay, and he proved a bunch of things about this, and some of them have a different version here with the probabilities included. Okay, so there's, yeah, okay, well, let me just and notice that actually all this structure, we have a metric on this P of L, but if we apply minus log or e to the minus x, we can get a metric on Q. So this is the metric on Q. Usually people, when they say Funk metric, they use this kind of coordinates. But this is precisely what you get when you just so you're up in your P of L. If you want to go down, so if you want to go up, if you're going to go from Q of L to P of L, you apply minus log. So you apply minus log to find yourself in P of L, and then you just write down what the equation is. And this basically is defined so that the dq of z prime is d of minus log z prime, and vice versa. So in other words, you can do everything with a multiplicative version also. And then in that case, it would also be a category, but it would be enriched over 0 infinity with model structure being multiplication. Okay, it would be the same thing. Okay, so the dual version, of course, where ui is greater than or equal to probability of ai given aj times uj. And let me notice that just as we had the unit isometric embedding from L to P of L, if I take e to the minus y with this metric that I define now, of course I get an isometric embedding into Q of L to have of L. Okay. Now, so this unit embedding puts this text inside my polyhedron, but where are they? Well, it turns out actually they're sitting very nicely as extreme arrays, because this is a polyhedral cone. Okay. So extreme array, you can just imagine the cone, the polyhedral cone, right? You just see the extreme array, but you can also consider what the formal definition is. It just means that if something is an extreme array, you cannot write it as a convex linear combination of two other things, not in a non-trivial way. Equivalently, if you have a polyhedral cone in Rn, it generates an extreme array a vector generates an extreme array if and only if it satisfies precisely n minus one linearly independent conditions, Q and Rn. And whatever, because the polyhedral cone lives in the multiplicative picture, but now we can minus log to the other guy, and we call this additive extreme array. And why do we call it additive extreme array? Because an extreme array is invariant under multiplication by lambda, but if you take minus log, it becomes addition by minus log lambda, so it's additively invariant. Okay, so we can call this an additive extreme array for the case of PL. Yeah, so this is just what I was talking about. And why, it's very easy to see why you would expect that they are extreme arrays, because if AI is less than AJ less than AK, let's look at the unit embedding of AK. Well, you have this triangle inequality satisfied as equality, which precisely means that, I mean, you know, this is y of AK sub I, and this is y of AK sub j, and this is dij. So this equation, xi equals dij plus xj satisfied on the nose. Therefore, it's you know, the inequalities become equalities saturated, so it's an extreme array. Okay, so these are extreme arrays, but not all extreme arrays correspond to text. There are more extreme arrays. So we have a theorem which explains what are the rest of the extreme arrays. And it turns out, let me tell you the answer. It turns out that the other extreme arrays correspond to lower sets, or I mean, you can take any lower set, for example, of this poset. So this lower set could be principal, generated by one text, or it could not be. It could be not principal. Okay, if it's principal, then we already know it's one of the images of the unit embedding. If it's non-principal, it's still an extreme array, but it just corresponds to a collection of text now. But the ones that it turns out that there's a slight variance from what you might expect is that if you take this lower set, and if you draw its Hasse diagram, it has to be connected. So non-connected ones do not give you extreme arrays. And this is a very nice. Okay, so you can make a very nice simplification. You can prove this theorem without the simplification, but let me show you the simplification, the most easy case. The easy case says that if you want to put in your game the empty text, you may imagine that this is a kind of innocuous assumption, but actually it's not. It's a pretty serious assumption, but which actually people who train LLMs haven't satisfied, but okay. If you have a zero, then because whenever you have AI less than AJ, you can always put in a zero less than AI less than AJ. This tells you immediately that this probability is a ratio of these two probabilities. In other words, all the conditional probabilities are derived from a global probability. Okay, so you can write down in that case the probability to go from AI to AJ. You can write it as the probability to go from A0 to AJ divided by the probability to go from AI to. Sorry. All right. AI to AJ. So it becomes a ratio. So when you have this ratio here, you can just take this to the other side, and you can rescale your variables, and then eventually you end up with new variables which are like that. And in this case, it's easier to see what's going on. But we don't need this assumption. You can prove this in general. So again, we have this we started with this metric space of texts. We end up with this polyhedral cone. It has extreme arrays. The texts are mapped to the extreme arrays, but the other extreme arrays correspond to some special lower sets. Okay. Yeah. Oh, okay. Go ahead. Sorry. Okay. Yeah. Okay. So we know exactly what the coordinates of any generator of an extreme array of a generator of any extreme array would be. Would be basically the characteristic function of the lower set. Okay. Of a lower set. Okay. Right. So okay. Yeah. Okay. And analogously for if you take p hat of a sorry, this is p tilde is a typo. It should be p hat. Corresponds to connected upper sets. All right. Now to understand better what this P of L and Q of L are, turns out we have to view them from the point of view of mid-class geometry. So this is completely expected. Well, I mean, it's not expected at first, but from the categorical point of view, what does it mean? It means if you have presheaves, you can ask the question, can you write them as colimits of representable presheaves? And it turns out you can, weighted colimits of representable presheaves. So this would appear, but the weighted colimits actually turn out to be just tropical mid-class addition and linear combination. So that's why you get it. But if you don't know about category theory, you're surprised, maybe. Okay, so let me remind you, what is the mid-class semifield? So you take minus infinity to infinity, and you consider, basically what you want to consider is logarithmic geometry. So log of x times y is log of x plus log of y. That's nice. So if you take logarithm of multiplication, it becomes addition. But the usual problem, of course, is what happens to logarithm of addition. Well, there is a cure for that, and this is this nice identity here, which says that logarithm. If you take e to the minus s over t, t is a parameter. Think of it as temperature. Or the parameter plus e to the minus t over t. Limit as t goes to 0, minus t times that, then it becomes min of s t. So this is the so this means that basically we define a new semifield structure by using as addition the minimum and as multiplication the sum. Okay, this is basically doing things logarithmically, and we have this temperature. This is very important because it tells us really that whenever we have a sum, a min-class sum, we can introduce a small temperature, write it as a sum of Boltzmann-weighted vectors. We're going to see that this is important later on. Okay, so first thing we notice is that what does our triangle equality tell us? It tells us that dik is less than dij plus djk for all j. But of course, if you take j to be I, then you get equality. So dik is actually the minimum of dij plus djk. Well, I mean, in this ring, this precisely tells you that d squared is equal to d. Okay, d squared, when you multiply a matrix, you take the sum of dij times djk, but here, the sum is the minimum, and the product is the plus. So it just tells you that d squared is d. Okay. So it just tells you that d is a projection, really. Okay. Now, if you have a projection, you know that the image of the projection is precisely the fixed part of the projection. And yeah, I mean, I don't need to prove that, but that's clear. But let me point out that what's going on here. The point is that if x is in P of L, then x is actually fixed by the projection. Well, let's just look at it. What does it mean? If I take b mean dx equals x, what does it mean? It means that xi is the minimum of dij plus xj. In other words, xi is less than or equal to xj plus dij for all j. Therefore, x is in this P of L. Okay. So it turns out that this P of L, we can view it also as just the image of this projection, the fixed part of this projection. Okay, so now we're in shape. Now we can play a different game because now we have new rules. So we can think of this basically, P of L is a polyhedron, but actually if you look at it from the min-class point of view, it's really a linear space. Okay, it's a linear space. And for example, now if I take any element, this equation here, what does it tell you? It just tells you that x is equal to the sum of xj times the columns. So x is really the column span of this matrix. Okay, so you can write any element as a linear combination of the columns, and these coefficients are just the coefficients in the linear combination. And so this is a min-class linear system of equations defined in P of L. And for P hat of L, so is the row span. So P of L is the column span, P hat of L is the row span, the min-class row span. Okay, as I was saying before, the reason why this should happen is because P of L is the presheaves, and any presheaf is the weighted colimit of representables. That's what we proved basically. Well, that's what we just proved, because weighted colimits are precisely min-class linear combinations. And any copresheaf is the weighted colimit of representable copresheaves. And so therefore, you get that P hat of L is the row span. So P of L is the column span, P hat of L is the row span. Okay, but actually keep in mind that if you take limits, it doesn't happen. So not every presheaf is a weighted limit of representables. Okay, we're gonna see that if we have time at the end. Okay, so the first thing to think about is to look at this now is, okay, I mean, initially we put all these vectors, I mean, imagine that, right? So if I have like 1 billion sentences, that's kind of the order of billion squared texts. Then I'm putting this in an order of billion squared vector space. Okay, so it's huge. But now what are the relations? That's the whole point. The relations are precisely given by, so the fact that the Dij is the minimum of Dik is the minimum of Dij, but the Jk, well, you can see that it tells you that it tells you this equation here. You can write down basically the unit embedding of AK as a linear combination of the unit embeddings of all the subtexts, and the co-unit embedding as the linear combination, mean plus linear combination of all the supertexts. Okay, so we see that basically this is a tropical linear system, and maybe we can think of the neural net as finding a solution to the system of equations. Okay, so it has a lot of constraints and it's trying to approximate the kind of solution because this will hold in general. Okay, and yeah, okay, it doesn't matter. This basically just says that we can write down concretely the generators for all the extreme arrays, but I don't want to spend time on that. Now, so as I said, this is a kind of linear space, tropical linear space, and to sort of further this point, I want to notice that this func metric that we said is a metric, directed metric, it actually behaves a lot like an inner product in a mid-class sense. So you can see it's an elementary calculation that is basically tropically antilinear in the first variable and linear in the second variable. It's like ZZ bar in a product. And when I say antilinear, it means that you have lambda 1x plus lambda 2y, comma z. This comes out as a minus lambda 1, and the min becomes a max. But in the second variable, it's precisely linear. So basically, you have this tropical linear space. This is a kind of tropical linear product. Yeah. So then let me just say one thing about duality. So the duality is kind of still it's kind of surprising, and there should be some sort of experiment to do to see the results of this actually, but I haven't gotten there yet. I mean, the duality is very simple. It just says that if xi is less than or equal to dij plus xj, then you can just take this to the other side, and this gives you that minus xj is less than or equal to dij plus minus xi. In other words, if dx is equal to x, then d transpose of minus x is equal to minus x. So this takes you from PL to P hat of L. So this is duality between extensions of text and restrictions of text. So it tells you that if you look at the whole space, even though individual vectors simply contain much less information, if you look at the whole space, you can recover a duality. Of course, you have to extend your coefficients to do that, but this can be done. Yeah, and so we have this two maps going from PL to P hat L and from P hat L to PL, which is just Px equals minus x and A of y equals minus y. And they turned out to form an adjunction. Okay, adjunction, what does it mean? It means that d of ax comma y is d transpose of x comma by. And if you write down what this means, is d of minus x comma y is d of minus y comma x, which you can prove relatively easily, where it holds. And so this gives you this basically equivalence between P of L and P hat of L. And you can check that A and B are actually isometries, and A and B are actually antilinear. Antilinear just in the way that we used it before. So, if you multiply by lambda, it comes out as minus lambda, and it becomes max and vice versa. Now, this may seem like a sort of trivial thing because you just have x to minus x. But remember, we're in the minus log space. So if we go to the multiplicative case, if we go to Q of L and Q hat of L, this duality is between z and 1 over z. Okay, so this tells you that if you do this transformation, you get this result. Now, I want to show you an example. Yeah, okay, duality coordinates, I'm going to pass. There's no point. We don't have too much time. So let's just see an example of what these things look like. Okay, finally, a very tiny example. Let's say we just have like, three texts, red color and red color. Okay, and so RC and RC. And let me start with the probability space first. So the probability to go from red to red is 1. The probability to go from red to color is 0, of course. And let's say that the probability to go from red to red color is 1/2. And then for C to R is 0, for C to C is 1, and let's say from C to RC is 1/3. And RC, basically, the only non-trivial thing you can do is just stay where you are. So now if I take minus logs, the distance is minus log of 1 becomes 0, minus log of 0 becomes infinity, and you get log of 1 minus log of 1/2 and minus log of 1/3.
Sorry. Why is 1/3?
Oh, I just showed these numbers. Yeah, just showed these numbers. Yeah,
1/3.
yeah, that's right. Yeah. Just take it out. Example. Okay, so now what do we? So let's start to apply our theorems. Okay, our theorems say that we know something about the extreme arrays. The extreme arrays should be basically corresponding to the lower sets and the upper sets, depending on the picture you see. So let's go for Q value. The extreme arrays correspond to connected lower sets. How many are there? Well, there's one generated by red, which contains just itself, one generated by color, which contains just color, and one generated by red color, which contains red color and red color. So there should be 3 extreme arrays. On the other hand, by the way, notice that if you take the one generated by red comma color, this one is not going to be, the Hasse diagram is disconnected because it's just 2 points. So this is not going to be there. On the other hand, if you take the upper sets, the upper set of R is RRC, the upper set of C is CRC, the upper set of RC is RC, but then now there is no principal one. Okay, so the first case where there's a non-principal one, and it's generated by R comma C. And now this one just contains RC and RC. So basically there should be 4 extreme arrays. And to draw them, because these are cones, we take an intersection with a unit simplex. This is what I call Q0 and Q0 hat. And these are the pictures. Okay, so this one is for, so the lower sets is this one. We said there's only 3 of them, and the upper sets is this one, we said there's 4. And so this one, the 3 correspond to the images of the unit embedding. And this other guy corresponds to this other extreme array. Okay, so this is kind of like a picture of what this would look like in a tiny situation. Okay. So let me just mention that we could also try a different approach where we approximate this infinity by some big number m, and then we draw the picture for that, and then we're gonna get this kind of picture that at the limit of m goes to infinity gives you the previous picture. So for example, here you're gonna get these guys and these guys to collapse to the sides, and you're gonna be left with the 4 points. So this is a duality between columns and row spaces of this metric matrices. Okay, it's actually a surprising thing. So but there should be a duality. It's not something which is completely obvious. Actually, Sturmfeld discovered that from a completely different combinatorial point of view, that you can get this duality between row space. I mean, so if you think classically, if you have a matrix, classical matrix, of course the row rank and the column rank are equal, which is the duality between row space and column space. And there's, because we have a usual vector space, it's completely determined by its dimension. But here it's a more complicated situation. Okay, so let me just now say one more thing. I want to explain, so because this L, you can always keep adding more and more text, right? You have some text, but you can add more text without screwing up the previous one. It's important to understand how this P of L changes as you add more and more text. Okay, So in other words, let's make this mathematical. Let's say we have probabilistic language model L1 D1. You extend this to L2 D2, which means that you have an isometry.
But I suppose you mean that the probabilities didn't change when I added more text? Or?
No, the previous probabilities didn't change. Yeah.
But they kind of do change today.
Yeah, I mean, I don't know. If you think of from the point of view of the model, you see the model is generating probabilities, right? You never calculate probabilities from any corpus because that would be infinitesimally small. So in reality, actually, you just want to model what the model does. The model produces for you this probability distribution, and actually, you're not even checking the whole probability distribution. You're just checking the most probable thing. So from that point of view of what the model produces, they don't really change because they have already been produced. So basically, if you have this isometric embedding from L1 D1 to L2 D2, then can you make an isometric embedding from PL1 to PL2? Yeah, the answer is yes. It's not actually it's surprisingly non-trivial to prove all that, but in a sense, if you have you just extend the basis, you have a subset of another set, you have a subset of a set, and you consider the corresponding generated vector spaces. One vector space is going to be inside the other. That's kind of what we're saying, but you just have to check a lot of things. And these are compatible with the unit embeddings. But not only that, the important thing is that the image of the smaller polytope is a retraction of PL of the bigger polytope. In other words, there is a non-expansive min-plus projection from the bigger guy to the smaller guy. The smaller guy is sitting actually on the face of the bigger guy. So when I add more text, I create a bigger polytope, but the previous polytope is sitting on some face. And then you can write down what this retraction is. I won't bore you with that. But the point I want to make is that there is an interesting special case. The special case is when you take the smaller guy to be the words. You can always put the words into any, just a set of words into any corpus. And if you do that, you end up, so basically, the projection, the image of the projection is what? Turns out to be a min-plus linear combination of the word vectors times these distances from the word vectors to the given text. Okay? So, and this is summed up over all words. In other words, I give you a text. Now, what I'm saying is that if I take the vector of that text, the unit embedding of that text, its projection, that is non-expansive projection, is basically a linear combination of the vectors of the words. Okay, and now, as I said before, when I have a tropical linear combination, I can get a Boltzmann-weighted linear combination. So this means that now, if I introduce my temperature
Can
T,
you go back just a moment?
Yeah.
So that, maybe you explained it, but that last one,
Yeah.
it means that the others are zero, or it means that they collapse each other?
What it means is that they're infinite, and therefore when you take the minimum, which is the sum here is a minimum, they don't contribute. Right? Because if they're not contained in there,
So it's zero.
yeah, that's right. Yeah. Okay, so now taking this equation here and introducing a temperature and making an approximation, we see that this projection of the text vector is going to be this limit, which means that this vector, the exponential of that vector, is going to be, so this is the exponential of the vector text vector, and this is the word vectors, and they're related by a Boltzmann-weighted linear combination. Okay, that's very much like what happens in the attention layer, because if you remember the attention layer of a transformer, the value vector of a text is a Boltzmann-weighted linear combination of the word vectors contained in that text. Okay, but this is kind of an ad hoc thing in the transformer, but we get this necessarily from this construction. It's a kind of necessary result of this game. Okay, yeah. Well, so the last thing, maybe just to mention a word, I said that, before we kind of expected
So
that.
could we go all the way tropical of the transformer?
No, not necessarily. It just means that the fact that we're considering probabilities.
No. No, I understand the statement that you made, but I mean, does this suggest that one could try to do just tropical transformers?
I think what it means is that we could reinterpret the transformer as it is as a tropical calculation. That's the way I view it. Just take the transformer that you have, but now you don't know what it means, but you can reinterpret it as some sort of tropical calculation. Yeah? And in a linear tropical calculation, which we know that if it's linear tropically, it would immediately give you Boltzmann-weighted combinations. That's the way I look at it. Okay, so just to say one final word, I mean, you may be surprised that you end up with a convex shape. Now, so let me tell you the way I think about this thing. So we have this polyhedral cone, and the only observable things are this special extrema rays, which are texts. Everything else is not observable, really. So it kind of corresponds to the hidden variables in a transformer. And given the fact that we get this relation that the text vector is a Boltzmann-weighted linear combination of the word vectors, this supports this point of view. So basically, you know, the thing is trying to learn somehow this this convex polyhedron, but it may be surprising, which actually could explain why it's possible to do it, because, you know, if you want to optimize, you don't want to fall on some crazy local minima, you know, you may need some convexity assumption, but it's kind of hard to imagine that just a convex object actually would do all the work for you. So in reality, there's a smaller object. In other words, what I'm trying to say is that there's a smaller metric space inside which we can isometrically embed our original metric space of language. But that space is a polyhedral cell complex, and it's highly non-convex. It's called the Isbell completion. Okay, so the Isbell completion turns out that it's sitting inside our polyhedron, and in fact, actually, it's the max plus. So remember that we said the min plus span of the columns is our polyhedron. Now, if we take the max plus span, it turns out to be this Isbell completion. Now, you may think to yourself, oh, what's the big difference between min and max? Well, it's a huge difference, because D is min plus squared. Min is min plus idempotent. It's not the max plus idempotent, right? So max plus is not idempotent. So in other words, okay, we can do this max plus completion, and it's this polyhedral cell complex. And actually, it's a generalization. It's a direct generalization of the Dedekind-MacNeil completion of a poset. So there, if you have a poset, you can consider the upper set completion or the lower set completion, but you can consider a smaller completion, which is the Dedekind-MacNeil completion. Dedekind completion it just comes from the way Dedekind defined real numbers, right? You take cuts, take everything which is bigger than something, and that's everything which is smaller than all these other things. And this is generalized precisely here by this Isbell completion. Well known not so well known, but definitely defined by Isbell back in the 70s. And it's funny because he defined it both for category theory and for metric spaces without ever noticing that they're really equivalent things. So this max plus span is called the Isbell completion, and there's an adjunction, and this is the fixed part of the adjunction. And this P of L is actually the min plus lattice closure, the min closure of IL. And it just reflects the fact that, you know, every pre-sheaf is the co-limit, is the weighted co-limit of representables, but it's not the weighted limit of representables. Okay, that's a standard situation. It's something to be expected. You expect from usual category theory that you may be able to write all pre-sheaves as weighted co-limits, but not limits. Okay, yeah. So this I of L is not convex, the polyhedral cell complex. It's sitting there, and you know, this actually was studied by people like Simon Woolerton, and it was used also in applied mathematics in phylogenetics. It was also used in some cases in phylogenetics with zero infinity values. Okay, and it generalizes the Dedekind-MacNeil completion. Okay, but this is more mysterious object. Okay, so I don't want to bore you. Okay, the overall picture is clear now. We started with this metric space. We transformed probabilities to distances. Then we isometrically embedded it, and we show how it sits in there. We show that it's defined by some equations. We have some dualities between extensions and restrictions, which are still mysterious. Yeah, okay, but there's a question?
This approach could be extended to any sequence or only texts.
Yeah, any sequence. I mean,
In time series.
you can take other data, like any data which is just sequences of text and sequences of symbols and probability of next word. Yeah. But I just want to finish with, with a word about sort of, so part of what the continuation of this picture would be. So the way I look at it is, this is a kind of standard picture in mathematics. I mean, so when we started this discussion, we said that, okay, when I have an algebraic object, I can consider the ideals, space of ideals, and then if my object is commutative, I can think of this commutative object as the space of functions. And just in case I don't want you to, if you haven't seen this construction, it's very simple, it's nothing complicated. Well, I mean, you can very simply see an example. Like, for example, if you take polynomials of two variables, what are the prime ideals? It's just the ideals generated by two variables x and y, say. Okay, polynomials of two variables x and y. All the prime ideals are generated by x minus a times y minus b. So therefore, the ideal defines the point A, B. So the ideals correspond to the complex plane. Okay, so these are, in that case, the ideals generalize. When you want to do no-commutative stuff, you have to go from ideals to modules. And it's not a real space anymore, but it's a category of modules. Now, modules are precisely presheaves. It's the same thing. Okay. So if we say that the syntactic category is the original category of texts, and the semantic information lives in this category of presheaves, this polyhedron, then we would expect that for different languages, because we can, to the extent that we can translate, I mean, translation is never, of course, perfect, but to the extent that we can translate, there should be an isomorphism and equivalence between these presheaf categories. Okay. Now, an equivalence between presheaf categories or between categories of modules is called Morita equivalence. So my hope is that, there will be some Morita equivalence. That will say that if I have two different languages, PL1 and PL2, then this should be Morita equivalent. Now, if you have a Morita equivalence, notice that it doesn't say that the original categories have to be equivalent, right? The categories of presheaves have to be equivalent. And the interesting thing about this categories of presheaves being equivalent is that now you can find invariants. Okay, so now you can find, so what would be an invariant? This would be kind of like, this would be what the nice definition of meaning would be. It would be something invariant between these different presheaf categories. And just to say one last word, I mean, usually these invariants are called Hochschild homology or cohomology. And in this particular case, there is a version of Hochschild cohomology. It's called magnitude homology, defined by Leinster and to some special Leinster and Schumann, in some special cases by Willerton. And so it would be interesting to study this and understand like what are these kind of invariants and so on. I mean, in a way, so the question is, what is the structure in such a semantic space? In a way, you know that if you have a transformer, transforming is like translating from Greek to English. Somewhere in the middle, there will be a common representation. The question is, what is the structure there, right? And so this kind of approach could find some sort of meaning variant, basically. Okay, all right, I'm going to stop here. Thank you very much.